your names yet, so hopefully we'll have a lot of questions. In the DUNE collaboration, I'm not used to having a 60 or 90-minute talk uninterrupted. I'm lucky to get 10 slides in, and I put up 5 slides and people debate them for 25, 30 minutes. So first I'm going to cover a little bit about me and introduce what distributed computing is, the scope of the DUNE problem, and then making it all work for DUNE. Here's my junior assistant, Leon Letterman. He's named after Leon Letterman, and he says, well, let's get to work here. He's going to get a treat for something. That's why he's licking his chops there. This is not a how-to talk. There is no lab session, but it's likely that some of you will have to either access DUNE storage and or submit a compute job at some point this summer. Who's got a DUNE compute account already? Show of hands. 1, 2, 3, 4. Okay, so some of you do this. Good. Near the end, I'll give some pointers to the existing DUNE computing tutorials, which take about 6 hours to go all through. Those tutorials will not work unless and until your advisor or supervisor jumps to hoops to get you access to DUNE computing. A lot of things have changed in recent months. Those tutorials are not quite up to date, but if you do get access to try them, please feedback with what it doesn't work. We've got to get them all working by September when we're doing our next big tutorial. About me, a little bit. I started out in physics, a small private college called Andrews University in Michigan. I changed my major 4 times. I started with physics. I went back up with physics by the time I was done. I also got a master's in computer science from Andrews University. And then went to physics grad school at Carnegie Mellon University in 1995. I did 5 years of postdoctoral research scientist at University of Albany at SUNY. I arrived at that group and we had 2 postdocs and a system manager and about 5 graduate students. Within 3 months, my boss fired the other postdoc and fired the system manager. I got to do all 3 jobs. I did the system manager job better than the system manager was doing it. So I've been in Fermilab ever since, from 2000 to the present, as staff in computing. I've been on the DUNE experiment since its inception in 2015. I am currently the co-lead of data management. I'm also the co-lead of operations, except my other co-lead in operations does not exist. I'm also in charge of facilities for DUNE US. And this means not only doing facilities, but finding the money to get to facilities. I'm hoping to keep working until I'm 75 or until the first beam in DUNE, whichever comes later. I'm not going to say how old I am now. But my specialty is doing the impossible with the wrong tool. I'm also old enough to have programmed COBOL for money, but that's another story. In 1984, my first visit as a student to Fermilab, I decided that was where eventually I wanted to work. 1986, as an intern in Argonne, I heard about the first massive underground nucleon decay detector, which would eventually become MINOS. In 1987, as a senior, the IMB experiment detected the neutrinos from supernova in 1987A. As far as I know, there have been no other reports of neutrinos detected between then and now. But hopefully, nature has cooperated and there's a supernova burst on its way to us about 9 years from now. Hopefully, I didn't get here too soon. This is completely deterministic. Whatever supernova is doing is going to see have already happened. We just don't know about them yet. In 1990, I came to Fermilab on an experiment as a graduate student. In 1992, I took a special topics in neutrino oscillation from Lincoln Wolfenstein, who was the man who basically came up with the whole idea of neutrino oscillation. When am I ever going to use this? We're the energy frontier. Fermilab is the biggest thing. When are we ever going to do neutrinos? Well, surprise. 1993, the SSC superconducting supercollider in the U.S. buzzed to dust, and thus began the whole transformation of the whole United States physics program eventually to be all neutrino physics, which it is now and is going to be for the rest of my career at least. So data analysis in 1990. This is me when I still had hair. One experiment, a straight line. This is all the people that were on the experiment. We all fit in one picture. in the very same hall where Leon Letterman found the Upsilon particle, in the same hall where later DUNE tested our first big 35-ton liquid prototype. We took a 1 terabyte of data. That was a lot back then. 1 pallet of 9 terabyte tapes. It was all analyzed on the mainframe at Fermilab in a couple of months. All Fortran code. About 50,000 lines of code in the entire experiment, I think less than that even. We reduced it to a data summary tape of 500 megabytes or so. All those people in the above photo came to Fermilab, do their analysis, finished, and went home. The internet was just coming available. Fermilab had it, but a lot of places still didn't. We had our experimental, we put up our experimental what is page in 1992. What happened? Why did we go blank? Isn't that good? Okay, we just did screen save. I guess I got to keep hitting this every once in a while. Okay, tape evolution. So when I talk about 9 terabyte tape, that's a 9 terabyte tape. It actually spins on a reel, goes from one spool to the other. One of them, max, would hold 170 megabytes. And when I say a pallet of tapes, that's basically one row of that shelf going all the way into the thing, okay? Now tape, I can get a tape with 30 terabytes raw size. Was just announced a couple weeks ago. Fermilab is probably going to be buying some of these in the next little while. So the tape has gotten, what, more than 100,000 times bigger in capacity, but only less than 1,000 times faster. This is going to be a theme that we're seeing throughout. Disk evolution, okay? We were very excited when we got a Run 7 disk on our experimental DAQ computer. I mean, it was a couple years old by then, but a gigabyte was a lot of disk in these days. That's a 5.25-inch drive. And we thought, we're great. I mean, this is a great thing to have. 3,600 RPM. Now the Western Digital UltraStar, which is not the biggest, but close to the biggest magnetic disk you can buy, 30 terabytes on one disk, but only maybe 260 megabytes per second of throughput out of one drive. So again, this has gotten, what is it? It's again a factor of 10 to the 5, order of 10 to the 5 bigger, but only maybe 100 times faster or so. So how has high energy computing changed, all right? First of all, we have much, much more capable data acquisition systems than we had back then. And experiments have just taken the track of writing everything that moves. That is certainly going to be the case of DUNE. We have DUNE is going to be in the case we're a mile underground. There's not going to be a lot of other noise in the detector. We'll be able to record every single radioactive decay that happens in the detector, every cosmic ray, whatever. We're in a state we'll actually need to actually write everything that moves. So that makes for bigger event sizes, as well as more events. From E760, we have about 2 kilobytes of event size. We're a very simple experiment, 1 track in, 1 track out. Collider experiments are the order of megabytes, a couple megabytes per event. 160 megabytes for proto-DUNE, which is running now, and 6 gigabytes for full DUNE. That's presuming that you read out the whole detector. And we have ways, a typical DUNE event won't actually use the whole detector, by the way. But so many, many more tracks per event, and much more time to reconstruct the event, even though our computers are much, much faster. And much more complicated algorithms to reconstruct it. I don't know if anybody has actually shown you an event display of what a liquid argon thing looks like already, but you have electrons. They don't have just one track. They make all kinds of fuzz along the way, basically photons and whatever. So it requires much more than using the single mainframe that Fermilab had to do the job. So that led us first to cluster computing and then to distributed computing, although in 1990, Fermilab did have a distributed computing department even at that time. Fermilab has at various points built our own computers. This would have been about the same time that the Apple Macintosh came out. Those were Motorola boards, but you could much cheaper buy a single board computer and put it in crates. That's what we did. We've used the VAX, digital VAX. We've used MIPS architectures, which are reduced instruction scale, RISC, reduced instruction set computing, right? And since 2006, we've used mostly the x86 architecture, but all of those things were clusters. So Fermilab has been doing cluster, even at the time that E761 was analyzing the mainframe, other experiments at Fermilab already had clusters done. And in the period of 1990 to the early 2000s, some of the stuff we were doing was the biggest anybody had done. The space that once hosted the mainframe in 1990 now contains hundreds of computers. If you go to the second floor of Fermilab Feynman Computing Center, you'll see probably about 30 rows of racks of computers there, and several tape robots on that floor. And we have 4 other computer rooms at Fermilab that are also full of computers, but it's not enough. We need computing elsewhere too. So there are 3 types of cluster computing. You notice I'm quoting a couple books here from the late 1990s, which is basically when this field in computer science really started to get going. But everything in that book is still very relevant for today. Very faster, high performance computing. A lot of very closely coupled machines with shared memory and things that have to communicate with each other. So you have one process that can only be solved by thousands of compute processors talking to each other. You have high throughput computing. This is 99-point-something% of everything that high energy physics does is what's called high throughput computing. It uses larger, what are the key features? It uses a large amount of CPU time and processes a large amount of data, but still is generally compute bound. So the metric is instructions, CPU instructions per byte of I/O. And of typical high energy physics computing, it's more than 1,000. The ratio is more than 1,000 to 1 of CPU instructions per byte of I/O. Yeah.
What does it mean to be compute bound?
Compute bound means that you're using your CPU all the time, basically, as opposed to reading a few bytes of I/O computing, Okay. You want to be compute bound in general, because otherwise you're wasting your CPU. You're just spending all your time waiting for your disk to read. Okay. Right. So eventually, if you make your computer fast enough, you won't be compute bound. But, right. So this work is sometimes called pleasingly parallel, because in general, the processors do not have to talk to each other. Each unit of work is independent. So you saw the qubit thing from the last talk. If one qubit goes, it just takes one qubit of however many qubits to take the whole thing down. Or in a high performance computer, one process going, if one of the 1,000 fails, then your calculation, you have to do it over. But here, if one of my 1,000 computers fails, I lose 0.1% of my work, and I can do that again, and all the rest of it because it continues on. This is what we mean by pleasingly parallel. Each unit of work is independent. And then there's also high capacity or capability computing. These are special purpose clusters. They're much rarer than the other two. There was a lot of these built in the early 2000s, the most famous one of them being at NASA. It was called the Columbia after the shuttle, which failed, but basically after the Columbia shuttle blew up in 2003 or so, the rest of the shuttle program, they basically built a computer that was fast enough to read all the video of the shuttle going up and calculate was it going to make it back or not. So extra high-speed internet to the file system, that's the main thing there if you have heavy database work to do. So this is a fairly rare thing today, but people still think about it. All right. So the DUNE Computing Challenge. So we're expecting to take a lot of data. You notice this graph goes out to 2040. Funding agencies actually require us to project out that far. And if you extrapolate out 600 This is terabytes, yes, it's 600 petabytes. If you add all our DUNE, you guys are calculating the total. But other experiments, such as CMS and Atlas, already have more than that on tape already, so this is not undoable. People have already done this. Fermilab experiments tend to read our tape a lot more often than the LHC ones do. But what is our challenge here? We've got to get it from point to point fast. I'll cover that in more detail a little bit later. We have to be prepared for whatever random access pattern the DUNE analyzers of the future, which is you guys, will come up with. I don't know what that's going to be, but I have confidence in my colleagues they will think of something that will do things out of order or make a very high bulk I/O or whatever. I'm just trying to build a system that will be prepared for whatever they think of in 5 years. All right? And then, like I said before, tapes and disks are getting bigger but not faster. We can store all this data easily, but can we read it back in finite time? So Amazon Web Services will sell you something called the Glacier now, which is actually a computer with a bunch of storage attached. They'll actually ship it to your location. You load it up. You ship it back to them. They put it in cold storage. It's powered off. And if you want to read your Glacier, you have to actually click in and then they'll go and mount it for you. So this is not what high energy physics is doing. This is not write once and read never. I should point out, I said that other CM experiments already have more than that. All the big websites, Google's, Facebook's of the world are 3 or 4 orders of magnitude beyond anything high energy physics ever taken. I mean, both Atlas and CMS just recently cleared exabyte this year. They've each of them got a zettabyte. In other words, 10 to the 18th bytes of data each. Facebook, Google, Amazon, whatever. I mean, they're way above anything that high energy physics is doing. But what they're not doing is they're not trying to read it often, read it randomly, and read it in creative and or destructive ways that break I/O systems. So I also have the disk thing here, and this is important because at the beginning of the DUNE collaboration, we set the limit that says we will not write more than 30 petabytes a year from the fire detector. They could write much more than that if they really wanted to, but they do have to do some kind of filtering, some kind of triggering, whatever, so that they don't write more than that. So what that means is that all the raw data from the DUNE fire and near detector we won't have on disk at once. We cannot possibly afford that. But you'll have maybe 1 year of raw data on disk, and the rest of it will be on tape. And then, well, I'll come to the computer. I think it's the next slide, yeah. But every year, at least, we will go back from the reconstruction we've learned, we'll reconstruct it all again. And so as the data starts growing linearly, you start seeing the amount of compute also start to grow linearly over time. The more data you get, the longer it's going to take to analyze. Okay, so yes, a lot of compute is needed. The kilo HepSpec 23 year. So first of all, what's a HepSpec 23? The spec organization is what specifies its industry standard of how performant is your computer. And there are, I think, about 16 different benchmarks that they use, 8 for floating point, 8 for integer. So for instance, one of those integer benchmarks is compile the Linux kernel. How long does it actually take your processor to just compile the Linux kernel? So there are some of those things that really don't track with anything that HEP does. So we picked only about 3 of those benchmarks out there, and that's where, from there we get HepSpec. And one HepSpec is one current CPU core of today is equal to about 11 HepSpecs. So when I talk about a HepSpec 23 year, that means it's running that core solid flat out for a year. When I talk about 1,100 of those, that's equivalent to about 100,000 if today's CPU is running full blast all year round. DUNE average is much less than that right now. Maybe we're averaging maybe 4,000, 5,000 all year round with peaks up to 20,000. Yeah, go ahead.
Yesterday was brought up, there's gonna be another detector possibly added, do those graphs include the, like, possibility of
These graphs are counting that there's going to be 4 by that time. And that's probably, in fact, optimistic because this graph was made before recent slides in the schedule. So, we have a pointer. Does it have a pointer on? Let's see it. Is there not a laser pointer in this thing? I'm missing it. It says it's got, oh, here we go. It's got a place for a laser to come out, but I don't see the button that makes it come. Oh, there you go. That was more off. Okay, fine. So, in the last schedule that was made, the 3rd detector kicks on about here. The 4th detector kicks on somewhere out about here, if that gets built. But I believe that we actually, when we made these, we were thinking that all 4 detectors were operational. So you don't see a second knee on the curve at this point. Eventually we'll have to modify the model some. There's a very complicated model that does our expected things, and it's basically all in a Jupyter notebook. And so we have certain inputs of certain types of processing that has to be done way out far in the future. Anyway, as I say, other experiments CMS let's already have more than that on the floor. More than 100,000 core CMS is. With other hats that I wear at Fermilab, I see they have quite a bit to do with the CMS pool, and they almost always have at least 200,000 cores active in their pool at any given time. And they can burst to double that, and they have capacity eventually. So we are here, just at the edge of the thing. Yeah, we are here. Now, around 2030 or so, well, actually around 2028, the high luminosity LHC turns on. By that time, CMS is going to need 10 times what they need now, what they have now. By that time, DUNE turns on about the same time, so we're going to be a crunch. In general, the collider experiments are going to be using a factor of 10 more than DUNE is using at any given time. So what we're going to need in 5 or 6 years they have now, what they need in 5 or 6 years is about 10 times more what they have. Okay. But what are challenges? We don't have enough space or money to put it all at Fermilab. Although Fermilab keeps asking DOE, please give us another computer room, and we've got the specs drawn up, and this is why we need it, et cetera. It hasn't come yet. Now, the second thing is not much more improvement can be made in Intel x86 architecture. So back when I was, a decade or so ago when I was doing this, you had to really allow for the fact that you had different generations of hardware, but for the kind of stuff we're doing, we have stuff that's, 8 years old, still running in production at Fermilab. It's not really all that much slower than the newest stuff you can buy. So we take the shortcut of saying a core is a core. Although hopefully we get a factor of 3 or so on this, so that in 2030 that's only 30,000 cores instead of 100,000. I'm hoping that we get that, but we don't know. So you can't make the transistors much smaller on silicon. Already at the level they're at right now, you're having quantum effects happening because the lines on the transistors are not wide enough anymore. Intel's working on 2 nanometer processes. GPUs are at 3 nanometer processes. You cannot go to once you get under 1 nanometer or whatever. You don't have a big enough structure to make it's not a bulk effect anymore. Surface effects basically are winning at that level. On the other hand, I've seen talks that 12 years ago said we were at the end of the x86 and 64 architecture then. So, expanding RAM requirements. This is the big thing for DUNE that the others don't have. That We have a huge individual event size. Right now, we can't even store it all in memory. But all the previous software expected that you had to. So the Dune code is very RAM intensive and is not. People keep on working and pulling it down, but then other cards explode, whatever. We're talking 2040. We do not know that Linux is going to be a thing 15 years from now. This is after the end of the Unix epoch. There are so many technologies that we rely on right now that could go poof. We could be doing something entirely different. I would hope that I was sort of disappointed. He says we're so far away from working quantum computers. I think we're going to need them, actually, myself. Right. So the components of distributed computing, for instance, Foster and Kesselman. Ian Foster is a professor at the University of Chicago. He was sort of the godfather of the grid. The grid, a blueprint for a new computing infrastructure. University of Chicago and Oregon basically came up with this for the first LHC experiments, which originally were going to turn on around that time and did turn on about a decade later. So the key here is the collaboration of computer scientists and physicists got together to build a distributed computing infrastructure, which is funded by European funding agencies, the National Science Foundation, Department of Energy. High energy physics was an early client, but by no means the only client. And there are many, many other scientific communities that are using it now. The American Museum of Natural History, just for example. A lot of computational biology. There are a lot of people who needed this and are making use of it. So what are the pieces? Compute nodes, which are often called worker nodes. These are actual computers where the jobs run. They're also known as the execution point. Authentication and authorization services, compute elements, storage elements, code distribution, databases, and networking. So I heard Ian Foster actually give a talk about this in 1989, saying it was all working then. The production grid only turned on 6 years after that. So I'm going to go over all those components in detail, one by one now. So computing hardware. This is what we had in the year 2000 when I started at Fermilab. This was the total computing power of CDF and D0. D0 on front, CDF in back. 50 regular desktop PCs each. When you could actually still use a regular desktop as a performance thing. Intel caught wind of people doing this and they made it not so easy to do. All right. 512 megs of RAM, 40 gigs of local disk, 100 megabits per second Ethernet adapters on the back. Okay. The latest node we bought is 2 by AMD EPYC processors, 64 cores, 2.87 gigahertz, 2 threads per core, but from 255 effective processors, 768 gigs of RAM, 2 by 890 system disk in RAID 1, and 2 by 3.5 data disk. These are SSDs. And a 10 gigabit per second Ethernet. All right. So trends in compute nodes. So in early 2000, we thought CPU speed would just keep on doubling every 18 months as it has. So 6 years, my laptop in 1994 was 50 megahertz. By 2000, we were at 500 megahertz. We're going the right way, right? Okay, no. The heat generated by a chip is going by the third power of the voltage of the chip, and thus is the third power of the frequency. Because the higher frequency you go, the more voltage you have to put on it. Single core chips would soon become hotter than the surface of the sun. You could have built a 20 gigahertz chip with that technology, but you could never cool it. So designers shifted to multi-core and many-core system. The cores do not go faster, just more of them. So we've never got more than, I've never run a chip more than 3.6 gigahertz at any point. But now we have 256 tasks hitting 2 disks instead of 2 tasks hitting 2 disks. Disks aren't built for that. Even SSDs are not built for that. Moore's law is reaching its limit. Transistor features only becoming a few atoms wide. That affects CPU now, but GPUs are also made of silicon. It will affect them too. It's just a little bit, they got a bit farther to go on that. Furthermore, much of the x86 instruction set is not used in scientific computing. There's business stuff in there. There's ASCII add, that you can take ASCII 9 and 1 and add them up in math without translating into binary. For just one weird example of many, many. So you've got a lot of chip real estate that is there and drawing power but not doing anything for you in scientific computing. So ARM chips, like is in your iPhone or on your iPad or whatever, or for that matter nowadays in your Mac, they're much more energy efficient. My Apple Silicon Mac has got probably 3 or 4 times better battery life than my Intel one used to have. Great on battery life, 5 watts per core rather than 70 or 80 watts per core. But finding the ones that do 64-bit math, not so common. The ones in your iPhone do not do 64-bit. So, cooling. This is one aisle of the Grid Computing Center at Fermilab when it was new in 2007, or the second room of that center when it opened. At the time, I think most of those nodes came from Dell. You see there's a grating in the floor there. So there was forced air under the floor. The cold air is shooting up out of the floor, being sucked in the fans of the things and being vented out to what's called the hot aisle. This is the cold aisle. This was designed in 2004 for a capacity of 1 megawatt in power in each of 3 rooms. And each one of those racks is about 70.2 kilowatts. But now you could put that same amount of power with just 10 nodes that used to take 40 nodes. Right. In one later room, we got it right, and we're sending cold air down from the top rather than bringing it up from the bottom. I mean, cold air sinks. We should do it. There's been, at Fermilab, there's been a long-standing bias that we don't want water cooling, mainly because the water cooling from our mainframe in the early 90s just kept on breaking and flooding our computer room. But we can't get away with it anymore. Our next computer room, if they ever let us build one, is going to have to be water cooled. Things are just too dense to make the efficient use of your building. You've got to water cool. The Argonne Aurora supercomputer, which is in a computer room that's not all that much bigger than this, has got a power draw of 60 milliwatts, and it is water cooled. And by water cooled, I mean they actually have got a cold and hot water hose going into every single blade of the server, not just something at the back. All right. Authentication and authorization, so some history. So the key to distributed computing is having what's called a federation of trust. So you can get the hardware, you can get the software, but if you don't have the people agreed on what you're doing, then you never make it work. All right? So the authentication is who am I? You have to have some way to present who you are in the distributed computing system. Authorization is what will the site let me do, given that they know who I am. So the International Grid Trust Federation was created, and in most cases, one per country, there's a certificate authority that can say, hey, this is Stephen Tim, and he's a good guy. We vouched there, we met him, we signed his certificate, right? And the International Grid Trust Federation says that they have to review the policy of your certificate signing authority and that you've got the right hardware. There are certain hardware requirements that you have to have. It has to be not connected to the rest of the internet. It has to have a hardware, security, all sorts of things. So each user is issued a public key, which is also called a certificate, and assigned by the CA, and a private key, which is just known as a key. And it's used not only for authentication, but for encryption of the messages. In grid trust, it goes both ways. So how many know what a HTTPS website is, right? They're all pretty much HTTPS now, right? So HTTPS website, any one of them has got a host certificate. So grid thing was two-way authenticated. I present a certificate to the site, and the site presents the certificate to me. If I don't trust their cert, or if they don't trust my cert, then the connection doesn't happen. And if you go away from the public-private key encryption module, you're no longer a grid. And we did go away from that a couple of years back. So in the past few years, everybody, all the good organizations have taken grid out of their name except for one. So there used to be called the Open Science Grid anymore. Now that it's still called the OSG, but it doesn't stand for Open Science Grid anymore. They just kept the acronym. It doesn't mean anything. The IGTF is now the International Global Trust Federation and so forth. So we just call it distributed computing now. That's why we just call it distributed computing again, because it really has moved beyond the days of the grid. Now, authorization is granted by means of membership in virtual organizations. So I have, and although there are no certificates, there's still the notion of things signing things, and it's now called a token issuer. We'll come to that. But still, DUNE has got to put the stamp on it and said this is one of DUNE. All right, so since 2019, the community has been shifting to use OIDC protocol for authentication, OAuth2 for authorization. Sometimes they just call everything OIDC. These protocols are closely connected. They've been the industry standard on websites for more than a decade. Developed at places like Yahoo and Google. OIDC asks you to choose an identity provider. So Fermilab has got an identity provider. Rice also has got, I think, anyway, I'm going to check. CERN has got, and all these things have got identity provider whereby if you signed in with your normal login, it'll say, okay, this is one of ours. I noticed that there's something called EduRoam network available here. So I don't know how many took advantage of it, but EduRoam doesn't have a total list of everybody who can use EduRoam. It has a list of institutions that will say so. They will talk to Fermilab, how you log, and then it calls back to Fermilab. It has me log in, put my password there, and then they take it on the result. Okay? Most Fermilab websites will come on what's called a single sign-on page, and the default is Fermilab, but it will take, at least some of them will take other identity providers as well. OAuth2 controls what scopes you have in your token. What can your token do? So authorization and authentication are sort of meshed into one technology here. In the what's called the WLCG schema, those scopes refer to what storage directories you can read, create, or modify, whether you can submit, list, or cancel a job. So there are compute things that are storage capabilities. There are three key types of tokens. The most common is what's called the access token. And that has the scopes I talked about. It has the expiration date, it has the issue date, and the key that it was signed with is in the token. And most importantly, it's got a little string of base64 encoded thing that actually is the mechanical thing that the other side reads to see if you're good or not. Then there is also the refresh token, and all that says, all that has in it is basically, again, another short base64 encoded string and a URL to say, okay, go refresh the token. And then there's also something that's less common, it's called the ID token. And you're working with DUNE computing, you will only ever see the access token because the refresh token is handled for you transparently. Typically, the access tokens are very short validity, only 3 to 6 hours. That's because there are web services all over the place that have the nasty habit of throwing your whole access token into the logs of the web server. the token is only used for the initial exchange, and then most things nowadays are encrypted not with public-private key encryption, but with symmetric AES encryption. Keep on hitting the thing that takes me out of the slideshow. All right, so next, batch systems. So generically, any batch system, first of all, why do I want to use a batch system? Say I want to do a process and I want to leave it running in my computer. Well, when my power goes out, chunk, I lose it. So I want to actually schedule the start and the end of it. Or I may have so much work to do, I can't just do it on one computer. Right? So you need a head node or nodes to keep track of the compute nodes and which ones are free. Right? You need a scheduler to decide which jobs to run on which nodes and in which order. You need a mechanism to launch the user process on the compute nodes, and you need a queuing system to keep track of all the jobs that have been submitted. I think this is generally 4 things that any batch system has got. So every distributed site that we run has got a local batch system. Most 2 common ones nowadays are HT Condor and Slurm. There's still some PBS, which is the parallel batch system in LSF, but that's quite rare these days. But most local batch systems do not expose their batch submission API directly to the internet. There are all kinds of reasons you don't want to do that. So you need some way to bridge that divide. And thus we have what's called a compute element. A compute element is an interface from the internet to the batch system. You accept a request on your API and you convert it to a job on the local batch system, and it gives you a way to get the results back from the batch system when the job is done. So there's a strong authentication system on the API. Nowadays it is tokens. There have been several completely different technologies over the years to do this. The common one is called HT Condor-CE, in the US at least. That's an extension of the HT Condor batch system designed to be internet facing. So you have HT Condor-CE that takes your token and it gets your job in from the internet, and it transfers it over to a local scheduler for you to actually run. So in the original grid design, only compute element and storage element needed internet access. You didn't need to have access on all your worker nodes. In current generation, it really helps to have the compute nodes have at least outbound internet network access as well. We've done it without it, but it's a pain. Storage elements. So storage element is designed to send and receive data from the wide area network as well as select computer nodes that aside read from it. If you need more than one server to handle the data, and you do, usually, then there has to be some way to coordinate all those servers into a unified namespace. And the current popular storage softwares of choice are Expert-D, Dcache, EOS, and Storm. The unpopular one, but sometimes you must deal with, is Lustre. Lustre is more for high performance computing. It is very good at having 4,000 computers all try to write the same file at once. It is not at all good at dealing with lots of small files. And in high energy physics, we deal with lots of small files all the time. All right. Expert-D was developed at Slack originally. It's an open source thing, and it allows you to federate a bunch of servers. You have, in fact, you can federate servers across multiple sites that way with Expert-D as well. It's also got a very good streaming protocol. Dcache was developed at Fermilab and DAISY. It's been the choice of Fermilab for the last 20 years and it's not going anywhere. And many other DUNE sites also use it. EOS is CERN's solution, and several other sites have also adopted that as well. EOS stands for exploration of storage, not end of service. And Storm, which is a European one. I don't see much of that in the United States. But all those federated systems can have back-end file systems. Expert-D supports several different back-end file systems. You may hear of what's called the POSIX standard, and that's a very detailed standard of all the various capabilities the file system should have. Generally, we don't need it, but POSIX specifies access control lists. It specifies deletion, modification, renaming. It's been 30 years since I looked at this standard. It's been a while. But generally, you don't need the full functionality. You can use things that emulate it. You can use a conventional Linux file system, which is pretty close. DUNE-TECH has what's called PNFS, which is the perfectly normal file system. So that can be mounted over NFS. It can be listed. You can copy files to and from it. What you can't do is modify an existing file. SFFS is becoming more popular. Ceph is nowadays owned by Red Hat, which is owned by IBM, but it's still open source. It's got an object-oriented store on the back end, but it presents itself to the world as a normal file system. It's slow, but it's redundant and it's reliable. And then some storage systems use a pure object store on the back end, such as Amazon S3 or emulations of it. And in that case, you don't store files as, you're not storing files as bytes. Any one file is a chunk of something. All right. Now, issues with planning storage elements. First of all, you have to pick disk. Magnetic versus solid state device. I say SSD, solid state device. We still call them spindles in SSD, even though they don't have a spindle. Magnetic is cheaper, bigger, and longer lived and more reliable, but slower, much slower. The total throughput, we talk about I/O, I say I/O per second IOPS. So you don't have to just figure out, do I have enough bytes to put everything? You have to figure out how fast can I read it back, how fast can I write it? Because you can get 250 terabytes by bringing along 250 USB drives from the backup store of Best Buy, but you will not be able to read it back any faster. You need performance, right? So the rule of thumb is that a magnetic drive is good for about 100 IOPS. Maybe that one I showed you, that real fast one I showed you earlier, might be a little bit better, but not a lot. Or 1,000 in SSD IO per second. To serve big throughput, you need lots of spindles. The current generation of servers we're buying have got 100 disk spindles in them. Right? And currently probably going to buy 10 or 20 of those this year. I think it works out to, what? About half a petabyte in one server box now. I thought we were good years ago when we had 1 terabyte in one server box. So there are two basic ideas here. RAID is the redundant array of inexpensive disks. They're not inexpensive. They can charge you extra to have RAID disks, but anyway, okay. And then JBOD, which is just a bunch of disks, right? RAID spreads all the data uniformly over a whole array of disks. So if I write one file to a RAID array that's got 10 disks in it, there'll be some piece of that file each one of 10 disks. And then one extra disk is there for parity bit. That's how it has the redundancy. So I can pull any one disk out of it, and we'll still keep working, and I'll still have all my data. JBOD has each file is only contained on one disk, or two if you have to replicate it. So that's the philosophy. This is what CERN has done for years, that they're all JBOD. They don't buy RAID controllers anymore. And any one file is only living on one disk. And on average, you get about the same throughput, but you'll see a distribution. So maybe your disk is good for 100 megabytes a second, but on one, all of a sudden somebody wants 5 files off of the one disk, and those go a little bit slower. And if only one person reading the disk, it'll go faster. I should have qualified here when I say 100, that's if you're doing random access. If you've got a whole bunch of things hitting. If you had a sequential read and you were reading a whole bunch of blocks at once, it would be faster if you were reading sequentially. But most of the stuff doesn't. most HTTP stuff's not actually reading sequential of disk. Right. RAID controllers are expensive, and then you have to declare some amount of disk as spare. JBOD is cheaper. The aggregate performance is about the same, but it's bigger variance response time. You have to keep a second copy of all the files. There is another alternate thing called erasure encoding, which I've never quite understood the math behind, but you can do it with less than a full second copy of the files. Now you have to also think about the maximum number of network connections. So how many different processes are going to be hitting this thing at once? Can we support that? And if they're reading slowly, then that's tying up connections somebody else could be using. And then matching network speed to disk performance. So, you know, I've got 100 gigabit networking on my storage machine, which I can get. Yeah, Aaron?
For the one square storage object for like Amazon, is there any difference between RAID and JBOD?
Amazon does. Oh, for object store. Well, I know from previous experience, Amazon doesn't do RAID. You haven't talked to them. What they actually do is sort of proprietary, but it's not RAID. Underneath the surface of an object store, it really still is all disk. I think it really doesn't matter that much, I think is the great answer. But I also know that Amazon doesn't RAID. So even if I have 100 gigabit networking, I won't get all of that by just moving one file. You have to move hundreds of files simultaneously to fill your bandwidth. So for instance, transferring our data across the pond from certain deferring lab, we have to have about 400 simultaneous file transfers going at once to use all the network bandwidth. And furthermore, the people that design these servers, that specify them for big labs, are worried now that as we're going forward, we can't actually get enough spindles behind it to actually fill the network bandwidth up. Code distribution. There's more code in DUNE than there was data in my physics experiment. And there's even more than that in the LHC experiments. 7.5 gigabytes per code release right now. And that's not even coming near detector, this is far detector stuff. And we make a release every week for more than 10 years. And most of them we don't decommission, they're still out there on disk. Our source code is stored in GitHub, all our current code is open source. Why not just load it into a container? It won't fit. DUNE didn't try this, but CMS tried this once on NERSC. They said, well, why can't you put all your code in a container? Okay, we'll put all our code in a container. Here's our 700 gigabyte container. The launch of the job timed out. Took 30 minutes, the job never got started. So we do use containers, let's be clear. Most of the actual code is getting mounted in the container from what's called CVMFS. Certain VM file system is what it stands for. Because it dates back to a project called CernVM, and originally they made this to distribute virtual machine images years and years ago. But it's an HTTP-based file system. It's mounted on demand only as it's needed, and it only fetches what it needs when it's first accessed. So of that 7.5 gigabytes of code, I don't really need all of that to run any one job. There may be a lot of subroutines that I never even call, and if so, I'll never actually load them. All right, individual, and they're cached in the local compute node. Now, this is important because, say I've got 128 cores on the compute node, they're likely all to be running my job at once, doing the same thing, because that's the way Condor scheduling works. It's a lot of similar jobs usually get scheduled together on the same node. So then I only, on average, I'm fetching 1 or 2 gigabytes of code, but I've now fetched it for 128 jobs instead of for one. And then it's cached there for the next job. And then also we're caching at the file, at the site level. So if a file is fetched once to a site, I can get it from the cache at the local site and not have to go all the way back to Ferring Lab to get it. Now, the other big thing that really saves us is what's called deduplication. So you can imagine that not every file changes in every release. Most of them don't. So if hello world.c is the same in every release, I'm only storing it once. I'm only transferring it once. So what starts out as what would be expanded to almost a terabyte of code on a flat system ends up being much less than that actually stored on the source and going out. All right. Two things that have nothing to do with CVMFS but are both important. DUNE is in the middle of changing to a new packaging system called SPAC. The old legacy one called UPS-UPD could have worked, but the maintainer said, no, we are not. They drew the line when we went from Scientific Linux 7 to Elma 9. They said, we're just not going to define the Elma 9 flavors in UPS-UPD. That's it, we're done. And so now we're all learning SPAC, which was started at supercomputers centers, and now it's spreading to Fermilab. DUNE is also writing a whole new computing software framework, which is called Flex. I don't think that will be covered here, but that's supposed to do the thing. Notice my colleague Anna Paula Vizcaya just went out of the room, but databases, you'll hear her talk this afternoon. I'm not going to cover anything about databases now, except for saying that with HTTP databases, we can cache them locally at sites too. And if all 128 of my jobs each have to fetch the same thing from the database, that's only fetched to the node once, and that's a huge thing of network traffic. Networking, the speed of light matters, especially if you're going from here to CERN. Most transport uses what's called the TCP/IP protocol. It takes 128 milliseconds to send a packet from Fermilab to CERN. Remember, the speed of light in fiber is not actually C, it's down about a third from there. And then the fiber is not going straight. And if you did the math of 6,000 miles, it does not take 128 milliseconds, but with all the switches, it does. Okay. And then it takes 128 milliseconds for that acknowledgement of the packet to come back to server before I can send another one and so forth. So half of the time, especially long distance, you're sending ACK packets back and forth. And the only way, again, you can use all your bandwidth, you have a whole bunch of packets in flight at once. And TCP is smart enough to know if ones are missed, it will retry, so forth. And in addition, many network clients are using multiple streams to transfer various pieces of the file at once. There's a trend that's happening. I haven't explicitly said it in the slides, but it's important. So we've had any number of proprietary network transfer protocols over the years that we've used, but there's a trend in high energy physics to go more towards communicating things. We don't write our own caching thing. We use HTTP for all of this because people already know how to cache that very well. And nowadays we're using it also to transfer files instead of older grid FTP protocols or whatever. So we're trying to get in a position where we're not dependent on so many bespoke tools inside of things. We don't have people maintain them anymore. All right. So for example, Supernova readout to full DUNE expect to be 400 terabytes, and we can only get it out of the mine at 100 gigabits per second. So it's going to take a few hours to get it anywhere. Right? Where do I get 400 terabytes from? It's reading out. I said it was 6 gigabytes before for a full. That's only for reading out the detector for 5 milliseconds. Now, for Supernova, we have to read it out for 100 seconds. So this is where the big thing comes from. But we have to be smart and send the most interesting parts, which are the front of the event, first to be processed. You have to plan your work based on how far you are away from the data. The detector reconstruction can stream from long distances and still be CPU bound. Untupling goes very fast. You need to be near the data. All right. I'm running a little bit behind schedule here. I only got about 6 more slides to go. So this is application now. And these slides are all going to be on the Indico. You can go back to them later. You don't have to write all this down in your notes. I want to run a set of jobs to look for an effect in the proto-DUNE HD data. Okay, first I need authentication authorizations. You're going to see a lot of links to DUNE-GitHub.io. This is the DUNE tutorial. It takes about 6 hours to get through. But once you get through the bureaucracy and technical steps to log into your computing, the actual computing is easy. You go 3 or 4 trainings also have to be done. Your supervisor has to contact your IB, who in turn contacts Maxine at Fermilab. She signs off. There's a form you fill out to get a remote access account. That gets you to log into the DUNE VM. Oh, that's not right. Not necessarily Fermilab, sorry about that. You get into our Slack instance. You see the mission setup part of that tutorial, which is what I've linked to here. Second, I need a place to put the output. If you're a non-privileged user, which all of you would be, the only place you can put output is scratch cache. When your account is made, there would be a directory like this made for you with your username. See the storage section of the tutorial, which is linked below. Need to find the name of the input data set. Okay, well, let's see the data management section of the tutorial and see the special Justin Russo and Medicat tutorial here. See also the brand new DUNE official data set webpage, which is done here at Rice. Realize and discuss that none of those actually give you the name of the cast. Bug me, and they'll tell you. We'll get that fixed shortly, but it's a raw data. Raw data will stay on disk for 2 years from the time it was taken in June of 2024, so it'll already be on disk. All right. Short digression on data management. It's an experimented operated service. It is for DUNE-2. We run our own data management. It's not generally considered part of distributed computing, it's sort of a layer above. But it's got 4 components. It's a data pipeline that brings raw data from the detector into DUNE. It's Medicat, which is a metadata catalog that tells us what's in the file and how was it made. It's Rusio, which is a replica catalog. It tells us where is the file, where is it supposed to be, and gets it there if it's not already there. And deletes it if it's not supposed to be there, by the way. And then there's a workflow system, which in our case is Justin. It can also be the data dispatcher. We keep track of file metadata, and that's a key step towards reproducibility of results. If somebody did a production 3 years ago, we want to know what version did they run it with, what operating system, when, what files did they run from, et cetera, et cetera. That's all kept track of. It's also key for data preservation and public data release, which we are mandated to do. I need to modify a bit of code to send along with my job. In general, you only have to build the routines that you've modified. You don't have to build the whole beast, which can take several hours. If you use the instructions tutorials to the right, you can upload a small tarball to CVMFS. It will be distributed with your job and then tarred when your job starts. I myself, by the way, have never gotten all the way through section 4 of the tutorial, even though I've been in the room where it's been taught several times. Now I'm ready to submit my job. Justin jobs have 2 components. One is the wrapper job, which handles all the finding of the input file and uploading the data storage is done for you. You don't have to do any of that. The job script is the user-supplied part of the job. Well, there's many templates to choose from. I picked one, but there's a whole directory of them there in GitHub of things to do. And that's a non-trivial example of something that will actually read a data file, run Larsoft on it, and send back the result. The Justin tutorial is there, and you can check the workflow at the Justin workflow page. I purposely did not live demo this. All of our examples are streaming the file, and that means we're only downloading as much of it we need at or slightly before the time that we need it. On a reconstruction job, you can stream from pretty much anywhere because there are many, many CPU instructions per byte. An analysis job, you need to be where the data is. So each compute element has what's called a distance from each storage element. That's arbitrary distance, which is physical proximity does not necessarily mean good network proximity. So is it allowing for network proximity? The user can specify the maximum distance the compute node can be away from the data. If you do that wrong, you can get a job that doesn't run. But also in streaming the file, there are a lot of times that you'll have a job that only says, give me this and this and this and this event. So you don't have to actually read the whole thing sequentially. You can grab these events you want, and it's done quite frequently. Workload management, which I did not cover earlier. Many experiments, including DUNE, use the glide in WMS. workload management and provisioning system. Is usually transparent to the user. DUNE currently has 39 compute sites and 17 storage sites. There's a factory that knows about all the 39 compute sites. A front end is examining our scheduler queue to see which jobs are appropriate for which compute site. And the user can also pick, say, I want to run at such and such a site. Then what's called a gliding script, which is a shell script that runs at the remote site. It launches a pilot job, and these refer to a virtual resource pool. What we had at the end is a unified resource pool. We call that the DUNE global pool in our case. It will all look like one resource. It will look like a unified pool across all these sites. Finally, help. I'm running near detector code, and it has this GPUs for the machine learning part of that code. Well, first of all, that's Matt. He's right there. And second of all, there are a few GPUs that are accessible on the regular grid with GPU flag. For more, you have to run at HPC Center. 3 different GPU manufacturers. I could go into much more detail here. I will not. But NVIDIA, which is the dominant one, AMD, and Intel. Right now, most DUNE code that knows about GPUs supports only NVIDIA GPUs, or it's only been tested on them. We're just in the beginning stages of trying to split it up. So even when DUNE uses a high-performance center, we're still mostly doing high-throughput computing. Individual processors are still keeping to themselves and not communicate with each other. But your goal first, make sure you do it right with one job, and then 10 and 100, and then scale up. Don't try to run 10,000 jobs at once if you don't know what you're doing. You get charged for 10,000 cores, whether you use them all or not. Nurse Pool Runner's got 1,792 GPUs, or GPU nodes with 4 GPUs each, and 3072 CPU cores. There's DUNE, which is the next generation we just announced, with ARM architecture, CPU, and a new Rubin GPU, which is 50 petaflops per processor, which sounds... It took a long time for FreeLab to get to 1 petaflop on our whole site. So this is huge. DUNE has already got people working on porting all to the various GPU architectures. HEP got lazy in the first couple of decades of 2000 because we had all x86 and nothing else. One operating system flavor, one type of hardware. Now we have to get our validation structure working again, make sure we get the same answer with all of those. I could tell you the story, but I won't, about how that burned me in my own thesis thing a number of years ago. So a few words about the cloud. High throughput computing can easily be done on institutional and commercial clouds. We have previously run jobs on Amazon and Google. But unless you're getting academic rates or free grant cycles, it's not particularly cheap. So at FermiLab HepCloud, we still have all the machinery there to do it, but we've pretty much kept it dormant. Original tests were done with Amazon spot pricing. At that time, it was 25% of the normal price. Now it's closer to 50. And FermiLab calculates this maybe a factor or 2 more than what we can do in-house. Also, funding agencies don't like writing checks to rent computers. They would prefer, at least FermiLab prefers to buy our computers and run them until they drop, well long after they're over a warranty. We just dropped our 10-year-old computers last month after 10 years of very venerable service. Cloud does, however, provide access to exotic hardware types such as tensor processing units, FPGAs, etc. And FermiLab doesn't have enough use case to buy one of them, so if you wanted to rent one of those, there's valuable for that. And inference servers is the main place you would use that. There's code in the DUNE code that does comparison is something a certain kind of electron or is it not. And before that, Nova had to do the same thing. So this is a long history of neutrino experiments of doing inference near the end of the job. Conclusion, this technology has changed a lot. Best practices don't, good policies don't. Good computing design grows out of good planning and good policy. No high energy physics experiment has ever got all the computing and resources it wanted, either in facilities or people. Nevertheless, they all managed to get through and publish, mostly by careful optimization and refinement processes. FermiLab does hire sometimes, and we place priority on getting good junior people in. Be ready for the networking question on your interview. It will be asked. Every interview I've been part of for the last 15 years, we've asked a question on networking. And that's all I have. I realize I'm standing between you and lunch. I'll take questions if there are any.